All right, important reminders, 2 of them. Number 1, your lab number 2 has been released, and I would suggest I walk you through about what it is about, the lab, very quickly, and then you should really try to struggle through the content. It's extremely important. I'll talk about lab 2 maybe after I talk about your upcoming written test 1. I'll just tell you what you can expect very quickly. If you look at the semester calendar, let me load it up very quickly. There we go. Okay. If you look at your semester calendar here, today is February 7. We're now here. Okay? So whatever we cover today is going to draw a closure on what's going to be covered for your written test number 1. You can expect to receive a guidance PDF from me by the end of tomorrow. I'll tell you exactly what you can expect, and there will be some verification task you want to do about your accounts. I'll write it down explicitly for you, so you can expect to receive it tomorrow. And then your written test 1 will be next Thursday during the class time, right? We're not going to meet here. We'll meet in Williams Small Center. I have already reserved the lab space over there, which is going to meet there. But once you see the PDF tomorrow, you will see everything. And I'm hoping to really give you guys some practice questions just for example, like what you can expect on the test. I'll try to give them to you by the end of Thursday or Friday morning the latest. All right, so you guys can definitely got roughly about a week to really get prepared. And you know what, you shouldn't really wait for me. From now on, you should really just review the math review lecture. It's definitely covered for sure in written test 1. All right, so that's about a written test 1. And about your programming test 1, that's after the reading week, I'll give you more information later. Okay. And about your lab number 2, let's take a quick look. I wouldn't really dive into the technical detail. That's something you're really supposed to struggle through. Come to me if you need any assistance, but you should really try yourself first. Okay, let me just give you a very quick walkthrough about what you're supposed to do. Okay. Lab number 2, we're solving something, the so-called celebrity problem. Anyway, the name is not important, but you're going to work with sets and relations. One thing you want to keep in mind, there will be 2 models you have to build. One is already given to you entirely. You just need to type it in, but just make sure you understand what's really there in the model. The second model there is something you have to create from scratch. The actual solution does not contain that many lines of specification. Not that much, but its meaning actually means a lot. So you want to make sure you really know what you're putting down for the second model. Right? You can also refer to the hints that's in your lab instruction. Let me show it to you. All right, it's due in about 2 weeks. And let's see. Okay, learning outcomes, that's fine. And assumption. Well, the assumption is, I tell you what, this is especially important about this summary document, which I already gave to you in lab number 1. That's about what you can do, what you can write in event B, the symbols for mathematical operation, like a relational image, relational domain restriction, and etc. That's something you're supposed to know for written test 1. All right? When you see the guidance, you will see some more clear guidance. Resources, that's the same. Okay, the background and problem. The actual problem about the celebrity problem is actually not very long. Only up to here, basically. Okay, that's the part you really want to make sure you understand. And it's a very typical exercise you will need to do. Given some informal description in English, and you're supposed to formulate what's really there one by one into axioms or invariants or even guards of events in the event B model. That's something you're supposed to do. And I hope you'll practice that for this lab. And this part over here is just one example to illustrate. If you can already imagine this part here without looking at that, just by looking at this rules over here, good for you, but it's okay. I included the example here just to illustrate to you how it works in a more concrete sense. And then if you go on to the task, there are basically 2 tasks, 3 you have to do. So number 1, I already give you entirely model 0, celebrity C0 over here. So I would suggest before you type it into Rodin, you want to make sure you really understand which of the mathematical equations over here, what they really mean. I try to draw some connection from, for example, certain axiom back to the original requirements over here. So this is something you have to make sure you really convince yourself. If you really have any doubts about why it is the case, you should really reach out to help. Otherwise, you get trouble, maybe later. Okay? Okay, and then for the second task over here, it will be a celebrity 1, right? Remember, we started with celebrity 0. This will be the second model, which you have to build from scratch. And I want to draw your special attention to this particular trace. When we ask you to really define, to declare 4 events, we got init, initialization, we got one event called remove1, another event called remove2, and we got a special event called celebrity. So these are the 4 events you have to play with. And that's something we might just be able to talk about today. Given the events with the guards and action, you ought to be able to somehow figure out what kind of traces I can have from the system based on their guards and action. We'll see if we can get there. If not, definitely Thursday, right? I want you to pay special attention to how this trace can be figured out. You'll see that's a general rule, and there is one trace here as well. So that's really one of the main learning outcomes from this lab. And as for task number 3, from the solution that the TA has developed, so there are actually a few proof obligations that really need some manual proof in order to be discharged. But for this lab, you don't really need to do any manual proof. However, I will give you a little bit more information about which proof obligation you should really watch out for, maybe about a week. Maybe after you struggle through task number 1 and task number 2, it makes more sense to talk about those undischarged proof obligation. For now, you can leave the task number 3 alone. But I'm going to tell you exactly what to do in about a week time. All right? And the submission should be no surprise. It's pretty much consistent with how you did it for lab number 1. Please make sure it's 12 noon, not midnight. All right? Luckily, we had nobody actually who missed that, which is good. Please pay attention to the deadline. All right? Do you guys have any general question about lab 2, which I'm happy to answer quickly right now? Somewhere? You got a question? You're fine? Okay, that's okay. But guys, start early, and I can tell you that the mathematics I just mentioned, they do take time to really digest. It might be a very nice case study for you as well for your math review lecture. We talked about many examples already, but here are just more. And for your lab number 3 and 4, we'll try to give you even more examples to play with. All right? That's a very important component for the course. All right, let me know. And for today, the lab at 1 p.m., I will be there in the beginning, but the TA will be there as well. Reach out to us if you really need help. Don't procrastinate. All right, that's my advice. Okay, so that's about these 2 important items. And other than that, I can start you fresh today about the case study, right? So far, we talked about math review. All the math you will need for this course has been reviewed. Just make sure you go over them thoroughly, and I'm going to assess you in written test 1 for sure. And for the first case study, I'm going to upload the slides a little bit later today. It's actually a very big lecture, I can tell you. We're going to stay here for at least maybe another 4 to 5 weeks at least. And the remaining part for the course will be just another slightly shorter case study called the FTP. But let's worry about that later. But this one here is the main one. It's actually such a nice example there. It's not too complicated. The idea is pretty straightforward once I walk you through. But there are many small components that need to be formulated about what kind of proof obligation do you have to formulate, and what kind of invariant do you have to write, and what kind of proof strategy should you adopt to really prove things. There are many things that can just be illustrated nicely by this small example. So don't be too frustrated that we're going to build a bridge for so many weeks, right? It's really a nice case study for us to learn many things. Okay, I'll always try to remind you what we have done so far, just to stay us on top. All right? Let's see what we're going to learn from this very huge lecture. We're going to, first of all, just recall what a requirement document is. I'm pretty sure you have seen this in your lab number 1. E description versus R description. Right? We're going to go over that first to begin with, to see what's really the requirements for a bridge controller. From there, we're going to see how we can build a series of models by refinements. And what a refinement is, and here refinements, don't think too hard at this point. If I say a model is a refinement of another, that means the refined model adds more detail to it. That's informal sense, very intuitive. Just add more detail. You try to be a little bit, try to do a little bit better in the refined model. However, when we talk about mathematical sense, there will be a fixed set of proof obligation that you should really discharge in order to prove that a model is a refinement of another. That will be the complicated part we have to get into a little bit later. For now, just understand refinement means we want to do better. adding more details. Writing formal specification, yeah, you'll definitely see predicates a lot, for sure. Okay? We wouldn't see, in the bridge controller, we wouldn't see too much about sets and relations. That's something you will do in the lab. When we finish the bridge controller, once we get to FTP, the second case study, you will see more sets and relation later. Okay. All right, so that's something you learned from lab 1. You got static part, also you got dynamic part, right? We'll see all of these to see how they should be defined to really build the bridge gradually. Constant, axiom, theorem, right? And remember in rodent, if you say a property or like some Boolean expression is not a theorem, that means it's an axiom, right? They don't really have that axiom label in rodent. And if you say a property, a Boolean expression is a theorem, then it should be subject to some proof, either automatically or manually. Okay? And dynamic machine. And basically, you can have some transition for the state machine. That's something else I'll get to visualize it. But we got variables, we got invariants, we got events, we got guards, we got action, right? So these are everything that you actually have seen in lab number 1. And proof obligations, that's really the critical part. So we will try to be very systematic to say, once you have got your model, what should be the way to systematically generate a proof obligation? And the way we do it in the lecture manually correspond to how they implement it automatically in rodent. So once we have, I'll try to maybe draw you some connection once we have covered certain proof obligation. We can go to rodent and see that's exactly what we learned, all right? And there are 2 things. One is about refinements, right? You want to prove that a model formally refines another. And also property, like an invariant property, okay? And this will be something I believe that will be new to every one of you. Have you guys ever seen like a sequence calculus before in 1090? Maybe no, right? If no, that's fine. It's something I'm going to teach you from scratch, don't worry. But sequence calculus, don't worry too much. It's basically like an implication in proposition. You just have to know what are the inference rules available for me to apply, and then how to really get used to the format. We'll do many proofs in class, or I can pass to you some reference you can also look into. We'll definitely do some in the beginning. That's more or less what we have to learn in the entire lecture, all right? All right, so let's recall a very important concept over here called correct by construction, right? So remember this little diagram here, right? Back in the introduction lecture. Let's review very quickly, right? I wouldn't stay for too long. I just want to remind you a few more points, okay? Let's go over bullet point and I'll annotate as I go. So you don't really want to directly reason about your source code, like a Java code or C code. It's just infeasible. There are too many details, okay? Think about this implementation that's already working or that's already executable. Usually it's too complicated for you to verify directly. So you want to build models by filtering out certain details, okay? So you want to remember the following principle. All these are models. All of these models. Description of the system under development by filtering out irrelevant details. And you will later see, to really build a bridge controller, you don't necessarily have to start with a model that's too complicated. You can start with something that's extremely simple. And that model there already covers some very important aspect of the bridge controller already. That's something we'll definitely see today. All right? And M0 is going to be the most abstract. Whereas the last model in the pipeline over here, it will be the most concrete. Somehow, or we say closest to code. Not exactly code, because it's still a model, right? It's still some abstraction, but just much closer. Think about every time, if you want to go from one model to another that's more refined, let's say if you go, let's say any MIMJ. If you think about what's happening over here. Over here, we simply say MJ, the later model over here, refines. Mi. You can also say Mi is refined by, right? So sometimes we might say either way. So just make sure the sequence, the order is really important. By Nj. How do we normally do refinements? Let me just mention something very quickly to you. When you say refines by adding, the most important part is about adding variables. All right? For example, the very initial model for bridge controller has only one variable, just one. When we get to the first refinement, we add 3 more. When we get to the next refinement, we add another 2 or 3, something like that, right? Just keep adding variables. The more variables you add, the more complicated it becomes for you to verify and reason about the system. But we start with something simple, okay? And as you add more variables, that means you got more axioms and also invariants, for example, to really verify about. That means more proof obligations to discharge. That's something we'll see. I just want you to have this general roadmap about where we're going. And in the case of the bridge controller, okay, so n here is usually some number, right? We start with 0 and then 1 and then 2. In the bridge controller case, there were actually n should be just equal to 3. That means we go from M0 to M1, M1 to M2, M2 to M3, and that'll be the last one. We got 4 models in total. That's what's in the textbook, which already made available to you. But in the lecture, we might only talk about 2 refinements. That should really give you sufficiently enough idea, right? Okay, let me see if I missed any point. Okay, we got requirements documents. Yep, of course. That's another very important point. When you are given some requirements documents, so you're given some requirements documents, it contains the E description and also contains the R description. We'll see concrete example today. Okay, very important for you to know. When you are presented the entire requirements document, there might be maybe, for example, 6 E description and 8 R description. The idea is you're not trying to reflect or encode every one of them into the initial model. That's not the point. What we want to do is we want to encode maybe E1 and R2 into M0 and prove something about it already. And then when we get to M1, we want to add maybe another E description, another 2 R description, and gradually. So the idea is as long as you can make sure, let me just show you another diagram here. Let's say here we got M0. Let's say we got M1, and then we got M2. That is a bit symbolic, but I just want to show you the idea. Let's say for the requirements documents, let's say we got E1, E description 1, E2, and also R1 to R3. So we got 5 requirements description together, right? So the idea could be we only try to encode E1 and R1. Here we try to do maybe R2, and here we try to do the remaining one. E2 and also R3. You can see we try to distribute the E and R description to be in different model. So we try to prove that each one of them in isolation can really satisfy the corresponding constraint, like an invariant or theorems, right? We can prove it. And what's also important is the direction over here. We do not just consider these models just in isolation, but also we have to make sure each one of them has the formal refinement relation. That's also provable, okay? So this is also something we need to prove, refinements. And also this one here, also we need to prove refinements. So ultimately, if you look at the whole pipeline, we should be able to cover all the E and R description, and also every connected model, they are also formal refinement of each other, right? That's what we need to do. Yeah, question? Very good question. So here, this is only like an example sketch. I'm just saying, let's say maybe we decide out of all these requirements that we ultimately need to cover in our model, we just decide somehow. We want to cover E1 and R1 in M0. Just happened to be the case. So in the bridge controller, we only decide to cover 1 or 2. So alternatively, you can try another possible model pipeline. You may want to say, I want to cover this one first rather than that one. It's completely designer's choice. Yeah, good question. Yeah, guys, let me recap. Very important. Given a number of E and R description, the idea is you don't really try to encode all of them into the M0 initial model. You try to distribute them into a pipeline of models. That's the spirit of the refinement-based approach. But in 4315, we go with a little bit more different extreme. For the model checking approach, you try to encode many requirements into a single model because it's a different approach to check. Anyway, for this course, that's the spirits you want to keep in mind. Okay. All right, let's see. Each model formalizes an external observer's perception of the system. Think about it's more like a public interface, right? We don't really have any private idea, right? Everything's public, okay? How the user is going to view the bridge controller, that's how we build a model, right? So this bullet point here, just principle, we'll see exactly how that's the case. And they're sorted with increasing level of accuracy. So if you look at this pipeline here, so this one is the most abstract, and this one here, MI, because it comes after M0. So that one is more accurate. It's getting closer to the coding. Okay, that's why it's more accurate. So they are in some way sorted from M0 to MM, from least accurate to most accurate. Oops, sorry, wrong way. Okay, first model and second model and etc. Okay, and every time if you want to prove and analyze your model, starting from the second one, the first one usually should be the easiest one. If you look at M0, M0 has no predecessor. That's the very first one. So once you have proved all the properties you want to prove about M0, that's it. You don't need to prove that M0 actually refines some other model. There's no other model that M0 can refine. On the other hand, starting from the second model, M1, M2, and etc. Not only that, you have to make sure the properties we define in M1 is satisfied, but also M1 refines M0. That formal refinement should be proved as well. So these are the two criteria, right? That's actually what's said in the slides. Two things. So just be careful. That's why I said starting from the second model, because for the very first model, you don't need to prove any refinement. That's a starting point. Okay. Right? You want to prove its property. Also, you want to prove that the preceding model, the predecessor, is being refined by the successor. All right. Another important point for you to see. If, let's say, I prove that the properties in M0 are satisfied, I prove that they're satisfying M1, they're satisfying M2. Let's say we have done these three. You know what? Let me write down very precisely for you. Because this will be the big picture clarification. Sorry. Sorry, sometimes my iPad just freezes. There we go. Okay, so let's say I got M0 over here. And then we go to the next level here. And here we got M1. And over here we got M2. Okay? So think about, we have to first of all prove all properties hold in M0. And of course, similarly, we have to also prove all properties hold in, actually it's all declare property. Because M1 and M0 and M1, they might declare different properties, right? All they declare. And similarly, for M2 over here, you want to prove that all the declared properties that are specific to M2, they're also proved. Hold in M2, right? Individually. And we also need to make sure, prove that M1 refines M0. And also need to prove that M2 refines M1. Okay, that's basically what I said before. Now, question. Is it necessary to also prove that M2 refines M0? That's a big question, actually, right? If we have to, then definitely we have to do another set of proof obligation, right? The answer is we don't have to, because the refinement relation that we establish between two models over here, they are transitive. Okay? Remember in math, if you say A less than B and also B less than C, automatically you know A less than C. The similar idea. Okay? The answer is no. Refinement relations are transitive. If I can already prove M1 refines M0, M2 refines M1, automatically I know M2 also refines M0. Doesn't matter how long the pipeline is. That's something very important for you to know as well. That simplified the matter a bit when we go over the details in the lecture. Okay? All right, that's pretty good. Let me clarify one more concept over here, and then we can move on to the bridge controller. It's something called the state space of a model. Think about the state space is just about the collection of all the variables together. The more variables you have, the larger the state space is. And the larger the state space is, the more difficult it is for you to consider the verification, right? And I'll give you one example in just one moment here. State space is the set of all configurations of each configuration will be all the constant and variables, right? That's what you declare, either static constant or the dynamic variables, right? And every time you want to figure out what are all the possible configurations, you want to think about what's the range of each constant or variable. For example, if the constant can range from 1 to 10, you got 10 possibility. If the variable can go with just a Boolean, then that'll be either true or false, 2 possibility. And somehow you have to multiply all the possibilities together, right? Just figure out how many combinations there are. Okay, so every time you think about constant variable, also think about what's really assumed to be true on the constants. Okay, and also some axiom you can also declare on the variables. I'll give you an example, just bear with me. And also invariant. Invariant is something you want to prove that it actually will hold for every state. Right? All right, let's now go over one example together. Okay, let's see this one here. And that's the definition. You can refer to it later. Okay, let's say we got some model, very simple, for some bank system. That you should really find something familiar since you have done lab 1 already. Right, let's say we got 2 constants and we got 1 single variable. All right. So what constant do we have? We have the credit limits, right? Remember the C. And also we got the upper limits, L, right? And also we got some accounts. So this accounts is simply a member of the partial function, right? So now we're using what we reviewed earlier. It's a partial function between the name of the owner and also their current balance, all right? And then we have some desired property over here. And this one here should also be quite straightforward to you. We say for every ID, that's the domain of the accounts, like the name of the user. Their corresponding account should be between minus C and also L, right? That's something we did in lab number 1. Now, it is very important for you to distinguish between 2 scenarios. Let's say over here, okay? This one over here is this an axiom or a theorem. Or in the case of theorem, we meant it's an invariant property that we actually want to establish. Axiom or this. We got two cases. I need to speak about both of them. All right? Based on what you learned from lab number 1, what difference is it going to make if we say this universal quantification here is an axiom versus if that's a theorem? Go ahead.
Axiom is
Oh,
you don't have to prove, whereas theorem you have to prove.
absolutely.
Axiom is true.
Yes, for sure. Yeah. So if this one here is actually an axiom, that means something we assume. And then assume to be true, and this can be used to restrict the state space. I'll give you an example very soon. Let me just write down the principle first. On the other hand, if this one here happens to be a theorem or invariance, then this one needs to be shown to hold in all possible states. Right? It's very important to distinguish between these two. Let's talk about the first one. Okay? And here the question is, we just want to give some example configuration of this initial model, right? So let's say this. For the first one, the axiom, all right? So here we assume that all the accounts in the bank have the legitimate balance between the minus C and also L, right? I'll just give you one example, okay? So here, this could be, let's say I just use like a tuple here. So let's say C, the credit limits, I'll just put it 100, okay? And also the upper limits, how about I'll put it 200, right? You can see so far 100, 200, they're both positive number, all right? And then I'm going to give some function. And function, remember, just a relation, set of pair. And this one here, I will simply do, let's say Alan is one owner. And then his balance can be anywhere between minus 100 to 200, right? That's exactly this. That's something I assume to be true. So any space that you can figure out should really satisfy this. It's assumed. You don't need to prove anything. There's no such a thing about violation of this axiom because it cannot be violated. It's assumed to be true. So let's say Alan here, let me just put 150. I'll put one more, and I'll make a remark. Let's say Mark over here, that would be another, let's say 199. So this one here simply satisfies the axiom. Okay, cannot be violated. And let me make one more note. That is, no state space, no states can violate this. So if I give you another one, let's say C is still 100 and L is 200. And let's say, oh, by the way, so this one is the accounts, right? I forgot to put the accounts over here. Okay, accounts equal to. And I got accounts is equal to, let's say only one person. Let's say if I put Alan here, I can go only down to minus 100. But let's say in this case, can I get such state space? In this case, no, I cannot. Right? Because this one simply assumed to be not part of the state space. So this one here violates, okay. does not satisfy the axiom cannot be, okay, how about this? Should not be even considered. All right, let me recap. In the first case, if the desired property here is axiom, that means any state space you have to consider should satisfy this in the first place. You do not consider anything that's not satisfying this. That's really the spirit for axiom. On the other hand, for the second case, so case number 1, and this is still case number 1. So let's talk about case number 2. Okay. I'll put case number 2 over here. Case number 2. Case number 2 means when you try to figure out a state space, you are not really constrained by this one over here. You can figure out as many state space as possible based on the constraint just on here about the types of the variable. And then if any one of them makes violate this, you got some invariant violation, like a proof obligation unproved in rodent. Right? That's really the difference. The state space allows. So, for example, let's say, let me use the same example. C100, L200. And also you got the accounts. Let me use the same example over here. So let's say you got Alan here. And then he has some limits, has some value that's way too low. All right? So now, this one over here, it is a possible state, but it violates the invariance, in which case you have to do something about it. But in the previous case, when it's an axiom, it's not even being considered in the first place, right? That's the difference. Okay, so this one here, invariance violation. That means somehow the model need to be fixed. All right. Yeah, this you can see this is a possible state based on the typing constraint, right? So we're talking about, okay, just in case you get lost. We're talking about case number 2. When this particular property here is declared as a theorem, that's something you want to establish based on your model. And in order to figure out all the states for you to consider, you just look at the typing constraint, the types of the variable. And to satisfy the type, this is one legitimate type. However, this one here has the balance over here way too low, which violates the invariance. In this case, you have to go back to the original model. Maybe you have to fix maybe the withdrawal events to make the guard maybe stronger and etc.
Okay, if I was the active, if I was the theorem, not the active, I'm thinking of the theorem. I keep on thinking that invariant is only the axiom that itself.
Yeah, think about invariant in our context, usually just a property you want to establish. Yeah.
Okay.
Yeah.
So invariant includes, right. The axiom and the theorem are both invariant. Sorry, I forgot that.
Mm-hmm. All right. So guys, it's only just to introduce to you about the idea about state space. First of all, it's about the combination of the variables you can have in the model. Number 2, either the property here is an axiom, in which case you assume all the states will satisfy that. Otherwise, you don't even consider that. There's no notion about invariant violation. But if you're treating this desired property as a theorem that you want to prove, then there is this notion about the state satisfying the typing constraint that might violate the invariance. Okay? Think about this a little bit more. Okay? I'll try to revisit this maybe a little bit later. Okay? But it's a very first exposure to how we distinguish between them. Any point you want me to clarify? Yes, go ahead. Yeah. No, C and okay. So here, if you say you cannot really have any C that being negative, because here you say C must be a member of positive. So that value is not even considered as a combination in the first place, right? All right. Okay, I would suggest, guys, for this second question here, just for now, how large is the state space? For now, let's not worry about it. Let me delete it, okay, for now. Okay, I'll revisit that point a little bit later. Yes, go ahead.
Sorry. So if you want to like see if it violates the state space, you would look at the accounts.
Yes.
Remember which one,
Yes. So think about this. You can think about this one here is a possible state space based on the constraint on the types, because C is a positive number, which is here. L is a positive number, which is also here. And accounts is any function from string to integer, which is also here. So now, should this be allowed in this particular model where this property here is actually invariant? No, it should not be, because you can see apparently this balance over here is way too low. All right? Yeah. Ryan.
If it is an axiom, it would restrict the state space more.
You restrict the state space more because you wouldn't even have to consider those pairs or those states that wouldn't satisfy the axiom.
So the size.
That would be smaller. Yeah. I'll try to give you guys maybe another better example, maybe another different example just to illustrate. But for now, just distinguish between axiom and theorem. Just for now. Yes. All right. Very good. Okay. And let's see. That's something we covered already. Configuration. Yep. So the more variables you have, the larger the state space is, and the more difficult it is for you to verify, right? That's definitely the case. And a model's complexity should be guided by those properties that should be verified against that model. We'll see that. When we have only a single variable for the initial model bridge controller, there's certain property we can already prove, only relevant to that particular variable. Not every one of them. All right, that's good. Okay, now we can talk. Yes, go ahead, please. Yes.
Do you consider faster as an axiom now, since because the variable will be violating the variance?
This one over here. Let me see. Are you talking about configuration 1 or 2?
Oh, sorry, this statement, the desired.
You know what? I think I should really change the wording. Let me change the wording. That should either be an axiom or that should be an invariant. Let me change the wording a bit for the slides, so to avoid confusion. I'll change that. Yeah. All right. Good. Let me see. Okay. So why don't we go over the roadmap very quickly, and then we can talk about bridge controller. But before that, we'll take a short break. Let's go over the roadmap quickly. Okay. And for the entire lecture, we're going to walk you through different models about a bridge controller. And it's called reactive system. Okay, that means the system has to keep reacting with the environments and also the user. Okay, look ahead. Have you guys heard about the notion about deadlock before? Maybe in your operating system course. So when we say reactive system, that means the system should never deadlock. That means there should always be some events that might occur for the system to evolve. If you ever run into a state where you cannot react anymore from the system, that means it's deadlock. And we're going to formulate this deadlock freedom notion formally later. That's for reactive system. Okay, with sensor actuators, so we're going to go over requirement document, and also we're going to see some strategy for refinements, and also abstract model. And we got 3 refinements in total, but most likely we only talk about the first and second for the lecture. Okay, before I show you the bridge, why don't we take a short break and then take attendance, and then we'll continue. All right, I think it's already ready for you to check in. Give me a moment. Start the class. All right, let me start a poll. There we go. All right, you can check in, please. You can choose any option.
Okay.
Any option.
State space model, like it has that plot.
That's okay. Yeah, just choose any option. Yeah.
Okay, so not an actual question, right?
All right. Any issue you guys have? Yeah, just come over. Yeah. If you got any issue, please come forward. Otherwise, I'm going to stop the poll. Okay. Yeah. Do you have? Yeah. Okay. Maybe you got a. Yeah. Anyway, so do you have a pen by any chance? Yeah. Just grab your pen. Yeah. Yeah. We'll take a 2-minute break. Not working for you?
Yeah.
Do you have a pen?
Yeah.
Yeah. Okay, sure. Very quick. Yes, go
I
ahead.
was just wondering for this, why is this valid if it's like an empty set?
Oh yeah, because remember this one here is saying it's simply just a partial. Yeah, yeah. Just find your name here and check mark and sign. Because here it's saying that it's actually a sorry here, it's a partial function between a string and also some integer. And we said before, the smallest partial function is
an empty
an
string.
empty set.
Oh, okay,
And
empty set, yeah.
let's say in the case where this is an invariant property, right? There's
The green ones?
the red one.
Oh,
Let's say that that's invariant. There's no way to violate that invariant in the empty relation. That's a trivial case.
Yeah,
Because you
makes
cannot find
sense.
any witness,
Yeah,
right?
yeah. Okay, okay, thank you.
Good.
Professor, I just
Hi.
have a question. So what I just asked you was
Yeah, go ahead.
here. So would we consider this an axiom or a theorem? Like
That's
for-
something, yes. Let me modify the slide a bit and I'll be very explicit.
Okay.
Yeah.
Okay, and then one more question. You said when we're going from one model to another,
Mhm.
we have to add variables. Do we only add one variable or
It could be
can
multiple. It can be multiple.
Okay.
At least one.
At least one.
Yes.
Okay, thank you.
Professor, I have a quick question.
Yeah.
Are there any books you could recommend that we could get more exercises
For,
other than the practice questions you're going to provide?
yeah, that's a good question. I think for written test 1, it's going to be mostly about math review, sets relation, etc.
I see.
I think any standard textbook that contains exercises about sets relation that might help. Yeah,
Okay.
and also what we did this, especially the example we discussed in class, they're very important. Yeah, and also some practice question will give you some idea. I think they can also work. I think for later tests and also for the exam, I think maybe reading some more details in the chapter might help. I don't think they contain any exercises, but I think they're
Because like I study better with
yeah,
exercise.
yeah, exactly, yeah.
versus whatever.
I would say try to make sure understand what we talk about in the lecture about different justification, different proofs. I think that should be okay.
Oh, okay. Thank you.
All right. All right, guys, 1 more minute, please. Okay, we'll start very soon, just in 1 moment. All right, let's start again. Okay. All right, bridge controller. Okay. Right, so I just chose some possible project for you, but no idea why you may want to do it. But Toronto Island, right? Let's say rather than ferry, you may just want to build some bridge between them. The idea is really about the notion about mainland and also island. So these are the 2 critical notions you have to be familiar with when we go over the example, right? This is just one possible example. Don't worry too much about this slide here, just to show to you that's how you can imagine. And let's now talk about the requirements documents. We're going to go over the E description and the R description, right? Let's remind ourselves the definition for each one of them. What's E description? It will be some atomic description. It should be simple enough, cannot be simpler, okay? it should be some constraint or assumption about the system's working environment. So typically, you would turn each description into axiom, typically. And sometimes you may want to turn them into the guards of the events so that certain events wouldn't be enabled if the guard is not satisfied, right? But typically, axiom on the constant. And very quickly, I will talk about our description, just remind ourselves the definition, and then we'll go on to go over the requirements. What about our description? It should also be an atomic description. It should be simple enough, but cannot be simpler. It should be some intended functionality and desired property. These are usually encoded as invariants that you really want to establish to make sure any possible involvement, dynamic involvement of your model should still satisfy the invariants. We'll see example. And also sometimes it could be the way the events will work, either their guards or maybe their action, right? So these are also possible. So our description typically will be turned into events or maybe some invariants that you want to prove, all right? For our bridge controller, let's go over E&R description, okay? But this is the diagram you want to remember, okay, throughout the lecture, okay? Pretty easy. You want to know that there's a notion about mainland. There's a notion about island. And there's a bridge between them, okay? At some point later, we're going to introduce traffic lights. But initially, in the simple model, interestingly, we don't even need the traffic lights. Because for the property that we prove, traffic lights are not really relevant. So that's why we can abstract the traffic light away in the initial models, okay? Right, again, mainland, bridge, and the island. So these are the three components you want to be very clear, okay? And let's now go over the requirements very quickly. Environments, number one, e-description. The system is equipped with two traffic lights with two colors, red and green. So we are talking about these two. But these two will not be in our model until the second refinements. So we don't need to worry about it just yet. The traffic light controls the entrance to the bridge at both ends of it, right? So if you want to go from mainland to the bridge, you have to look at these traffic lights. And let's say if you actually want to go from island back to the mainland, you have to wait for these traffic lights, all right? Okay, sorry. Okay, so also we talk about the traffic lights. So environments constraint 1 and 2 are not immediately urgent for us to model just yet. So cars are not supposed to pass on a red traffic light, only a green one. That was interesting, this environment constraint here. Because realistically, you can basically, let's say if you don't have environments 3, let's say you don't have it, okay? You can build eventually some model that will ultimately satisfy all the requirements over here. But the model itself may not be realistic because what if the driver does not obey the traffic lights? In that case, for example, you cannot maintain the bridge to be one way anymore. You can, if you prove that your model is collision free, you cannot hold that result anymore because the driver can just disobey the traffic lights. So that's why this assumption here is so important. This is something that we don't really encode directly in the model. We're just saying that once we have proved the result about all the critical property, it's under the important assumption that drivers, they don't try to disobey the law, the traffic light. This is really important. Okay. So this here, without this, verification results will be unrealistic. Okay, just remember. Okay, the next one. The system is equipped with 4 sensors with 2 states, on and off. And for the sensors, we will not really get to there until the final refinements. If we get time, we might get to it, but for now, we don't need to, okay? But sensors, it just sound, you can think about adding the notion about traffic lights, you have to give 2 variables, one here and one here. If you want to talk about 4 sensors, that means you need another 4 variables, right? Every time you want to handle another constraint, you have to add more variables, okay? And that's just more about the sensors. Okay. just more. The sensors, but we don't need to worry about them just yet. Actually, you know what? This one here is interesting. To detect the presence of a car entering or leave the breach. So think about this one here. We do have a little bit encoding of that. I'll give you a little bit look ahead. Encode this by counting the number of cars entering or exiting the mainland. Okay, so you can think about every time we have a car going from here to here, if the car is allowed to really go, then we kind of increment the counter by 1. And if the car successfully leave the island and go back to the mainland, we might just decrease by 1. Right? That's what I meant by maintaining some counter. Right? What about the requirements? The system is controlling cars on a bridge connecting the mainland to an island. That one is to say, we just need to have the notion about the bridge connecting these two. Right? We'll see that in the model soon. The number of cars on the bridge and island is limited. That's really the most critical one. We're going to use that for the initial model. And let's read this more carefully. What should be limited? The number of cars on the bridge and the island. That means we are talking about cars in the island and also the car that's already on the bridge. These two together should be limited, not individually. Okay? So this is requirements number 2. So this will be requirement number 2. So for requirements number 2, the cars in these two parts should be limited. Okay? But the requirement itself doesn't really say, should we really constrain the number of cars in the mainland? It doesn't say. So it can be anything. All right? Okay, just unlimited. The final one, the bridge is a one-way or the other, but not both at the same time. So that means if I currently have a car going to here, I should not have another car going to here, right? That's easy. And that's like a safety property we have to make sure it's established for the model. A very quick walkthrough about the requirements involved, but we'll only try to encode 1 or 2 of them in the very initial model. That's the spirits about refinements, which we spoke about before the break. All right, any points that's not clear to you? You want me to address a bit further? Yeah? More realistic, yeah.
So what kind of environment we need to add to make our system?
Yeah, think about this part over here, that the fact that the driver will obey the traffic lights is not really something we'll encode into the model. It's like the extra assumption we are making. So let's say at the end of the day, let's say you manage to discharge all the invariance preservation, all the proof obligation. You want to say also, by the way, so all these together with one more assumption, that drivers will obey the traffic lights. Otherwise, it'll be very difficult to really model. Oh, what if the traffic, let's say this. Let's say the traffic light is currently red, let's say. If it is currently red, if we do not have this assumption, what's going to happen is, even though we are already restricting the flow of the bridge and the island over here. So we say, okay, right now, in order not to increase any more cars onto this part over here, so this is a red light. But if the driver doesn't really obey, then what should we do, right? Should we have another kind of mechanism to block them? So that will just make your model more and more complicated. That's not something we want to get into. We want to say, once the light is already red, the driver will just stop here. So that's allow us to do some flow control right away without considering further. Make sense to you?
How about if a driver want to go from inland to the Axiom without using the bridge?
Well, that's not our consideration then. Here we're only considering people or drivers who actually want to go from mainland to island and vice versa. If the driver want to go from mainland to island by, I don't know, helicopter, that's not our system's concern, right? Yeah, sure. That's another way, which we don't care, right? No. We only care this particular bridge. That's what we are building. Other ways of commuting from the mainland to the island, we don't care. That's not what we're building, right? All right, good. Yes, Adam. Oh, I see what you mean. So typically for the requirements, you will hope that the constraint over here is fixed. Because anytime you have to introduce a new environment constraint, that means you got to add some maybe new axiom to your model. And what if somehow the new axiom contradicts with one of the existing environments, in which case you got all the axiom evaluated to false. Then in that case, you got some false system to begin with. Right? So I would say, yes, it is possible that at some point you may just want to add another environment constraint, but you better make sure that one there is still consistent with what you got so far. Yes. Yeah, for sure. All right, let's move on a little bit. Okay. All right, E description and R description. And that's the diagram. And for the very initial model, we're going to make this diagram even simpler. You might think this is already simple. We can make it even simpler just for the initial model. Okay, very quick slide just to summarize about refinement strategy. And for the very initial model, M0, which we'll talk about a bit today, and maybe most of Thursday and possibly beyond. Okay, initial model, we call it M0, the most abstract model possible for the bridge controller. And for this one here, if you go back to requirement number 2 over here, I'll let you refer to it maybe when you study. The number of cars on the bridge and island is limited. So that we are only going to handle these requirements only. As far as this requirement is concerned, for example, traffic light is not necessary. Right? And also number 2, sensors are not really necessary. We just want to keep track of how many cars are on the bridge and the island. That's all we need. That'll be the initial model. And the later one is just for your information. I'm not going to go over them, but that's something you can go maybe come back after we have gone through maybe the refinements, the first and second refinement later. Okay, but you can see, not surprising about the pattern I mentioned to you before. For each one of them, we just try to add some more E or R description over here and more property to really prove. Right? That kind of corresponds to what we said before about the pattern. And correct by construction. We want to make sure every model 0 itself satisfies all the property and provable. Starting from model 1, we want to make sure not only that the property will satisfy on the model itself, but also you will formally refine model 0 and etc. Correct by construction. Okay. Okay, M0, right? And before I show you that important diagram for M0, let me just come back here. Remember what I drew over here, okay? If you recall requirement number 2, that one says the number of cars on the bridge and the island should be limited. So that means as far as requirement number 2 is concerned, we don't really have to distinguish between a bridge and an island. All we care about is how many cars in total are on here and also in here. Okay, let me make that remark. Also, this requirement number 2 I'm talking about, makes no distinction. Oh, sorry, let me write properly. Makes no distinction on the island and also the bridge. So for the very initial model, we're going to consider the islet and the bridge as a compound altogether. We're going to call that island-bridge compound. So what you guys shouldn't really get lost is how we derive this particular abstraction. Let me repeat again. for requirement number 2, you only worry about this number of cars in the breach and the island together. That one should be limited. So that means we don't really have to distinguish between island and breach, only the number of cars in total over there. Okay? So let's take a look at the initial model. Good. This will be, yeah, we don't really consider the breach itself in isolation, but the breach island together. And also no sensor, no traffic lights, nothing. Requirement number 2, and this will be the diagram. Okay, let's take a look at the diagram. Here. All right. So you can see here, no breach, but just island and breach considered together. All right, breach is not considered in isolation anymore. That's something to really note. Okay, so here, the notion of breach is abstracted away. All we consider is this number of cards. This is going to be some variable that we have to declare in our model. Okay, this is going to be called n. You will see that declaration in the model. Okay, for this compound over here, for the island and the breach, we only worry about n. Okay, let me just give you a little bit more illustration. It is so important to notice that. Let's say we still got this island here. Let me just be consistent. Let me just island, breach, and mainland. Okay. Imagine this. If this is the island, this is the breach, and this part here is the mainland. Realistically, let's say there are 3 cards over here. So I'm sorry, I'm not sure how to draw the car. Let's say 3. Over here, in the island, there might be 100 cards. Right? Realistically, we know that there are only 3 cards in the breach and only 100 in the island. As far as model 0 is concerned, what should be n? 103. That's the abstraction we are making. We don't distinguish between where the card comes from. Either it could be in the breach or it could be on the island. That's a very critical insight into it. Okay, just from this part over here, think about 103 cards on the island breach compound. All right. And the textbook like to give you some analogy about what we're doing here for this very initial model. Let's say you're trying to observe the system, the breach controller, the island, breach, and the mainland from very high on the sky. In that case, you wouldn't be able to see that breach anymore because it's so high in the sky, so the breach becomes very small and invisible. That's why you're only seeing this island and breach compound. That's an analogy. If you want to try that, try. Otherwise, I think this might be a better explanation about what's really there. But we don't distinguish between where the cards come from. Can be from the island, can be from the breach. For the initial model, we don't care. All right? Any question about this abstraction over here? For every model that we're going to build, we ought to understand what's really the rationale for the abstraction behind the scene. So here, that's what you need to know for M0. All right? If you guys are okay, let's look at the state space for the initial model. What variables should we get? What constant should we declare? And state space contains 2 parts, the static part and the dynamic part, right? So these 2. Let me go over the bullet. Let me see here. Okay, static part will be fixed and can be, remember the keyword C's, S-E-E-S in the rodent. That's what we did for the banking example. So that will be some constant. So here we got some, let me just show to you directly. That might be just easier. Okay, so there are 2 parts over here. And remind you, we are only trying to look after this particular requirements for M0, okay? And there are two parts for the model, okay? The static part is something that's always fixed. So we have some constant D. The D here denotes the maximum number of cards in the island and the breach. And we say that D should be a natural number. And remember what natural number is, right? Can be 0, can be 1, can be 2, and etc. That's the static part. It's easy as that. We just have some upper bound for how many cards you can accommodate in the island and the breach. What about the dynamic part over here, right? We just have the variables over here, and initially maybe 0 when there's no card in this island and the breach. As we actually get more and more cards going from mainland to this compound, of course, n can increase. As we get more and more cards that want to leave from this compound back to the mainland would decrease as well, right? You can see this just increasing and decreasing of the n to really model what's happening. That's the simplest way to perceive this model. All right, so here, this n here is the current number of cards in island and breach. And we say that n should be also a natural number, and also we got some very important invariants over here. That's a simple one, so we don't really need to give you some time to come up with it, right? This is really, really important, right? This is corresponding to requirement number 2. So think about we are keeping track of how many cards are already here, which is n. There is a fixed constant d, and we want to make sure n is less than or equal to d. That's what we got in this initial model. All right, and you might be wondering, what's the ML out and what's the ML in? We'll get there when we get to how we can modify, how we can change the state variable. The way we change the state variable is by occurrences of events, like a withdrawal, deposit, etc. But in this case, we got an event called ML out, another event called ML in. But we'll get there. All right, any question about how we build a state space consisting of the static and dynamic parts? Pretty simple, right? Okay. So far, it's pretty straightforward, but when we get to how to prove certain property, it gets a little bit trickier, but we'll get there. Okay. We might just be able to move on to, transition. Let's do one more. Let me see if I missed anything here. Constant, axiom, okay, axiom soon to be true, maybe used to prove other theorems. Dynamic part, and also we got variable, okay, and then we got n here, the two invariants. Oh, one thing very important to also talk about, the naming convention for the axiom and also invariants. We are using the same naming convention as in rodent. For example, when you look at this, right, the naming convention, the AXM tells you it's an axiom. That's obvious. What about the 0 over here? That tells you it's actually for model 0, or M0. Okay. And the 1 here tells you it's axiom 1. And the next one can be AXM 0 underscore 2, right, in the same model. So you ought to really know what these numbers really mean, right? They try to denote systematically what we are dealing with. Similarly, whenever you see IMV, that stands for invariance, some theorem you want to establish. And 0 here is also about M0, the model, initial model. And you can see 1 and 2, that's about invariant 1, invariant 2 in the same model. And later on, when we want to prove about refinements, you ought to really consider invariant and axiom from 2 models. So you need to have a way to distinguish between them. So that's why the naming convention here is so important. Okay. All right, Let's see. That's good. About the invariant should be established and maintained. I will talk about this point. I just need to draw some diagram. But for now, let me introduce to you the events very quickly. And then I think that will be it for today. And I'll pick up from this point next time. But let me just talk about the events that we need to worry about. Right, so this part here, again, I put everything together, right? We just remember all the relevant stuff should be here. The requirements that we are worried about for this initial model, static part, dynamic part. Also, that's the abstraction we are using for M0, right? So now we got two events over here, ML out, ML in. Conceptually, whenever there's a car wanting to leave the mainland, in that case, it's going to be represented by ML out. A car leaving the mainland, ML, mainland. And whenever you have an occurrence of the events, MLN, a car back to the mainland. All right? Really important to see what these two events really mean. And obviously, remember we maintain some counter over here for n, right? If we got ML out occurring, in that case, we should really increase n to be n plus 1. Agree? And if we actually got a car going back to the mainland, in that case, we should really decrease n to be n minus 1. That's the idea. That's something you have to encode into the action of the events. Let's take a look. So now you can see we got two events here, ML out and ML in, right? What's really within the begin and end are the actions for the events. Okay, that's something we also spoke about in lab 1. So this one over here is about action. This one here as well. And notice that what's really missing here? We don't seem to have any guards for the events, right? When we don't have any guards, what does it really imply? Does that mean the guards should be treated as true or false? If you treat them as false, that means none of the events will be enabled. Both of them are disabled. That means you deadlock the system right away. So treating them as just false may not be the way to go. True. Okay, if we do that as true, that means the event will be enabled all the time. All right? All right, let me just mention this. Okay, I'll just take 2 more minutes and I'll let you guys go. And then we'll continue from Thursday. So here, you want to really know missing guard. Implicitly true as the guards. And that's a very important consequence. That means events are always enabled. Okay, so whenever you see any model you're given, if there's certain event that's always enabled, it's almost like a no-no. There should be some constraint in the guards to say this event is only enabled under certain circumstances, not always. I'll get to your question. An event should not be always enabled. It should not be always disabled either. There should be it should be contingency, right? Contingent. Yes, go ahead, question. Mm-hmm.
But you only need to check whether, so you only need to check the condition whether you want to bring in cards into the virtual.
Yeah, so the short answer is, because in general, the actions that's inside the events may be multiple. So you cannot say, I only have guards for a specific action. No. So whenever you apply the guard for the events, it's applicable to all the actions together. So you cannot really apply just to a single action. So here it's pretty simple. We only got one action over here, so it's as if to only this action. But you should think about, because the action part contains only this one, so it's applicable to the entire thing. Okay, Ryan.
Doing without guards is making everything axioms in general in the machine. It's like if you define all the conditions axioms.
Not really, because when you, very quickly, so, and I'll let you guys go. When you declare axiom, it's mainly constraining about a constant. But when we talk about events, events are ways for you to modify the variable value. So they are kind of different. So you want to make sure your events should be properly guarded. So sometimes you may modify your variable too much, such that the resulting state is going to violate the invariance. That's something I will show to you guys on Thursday. Guys, thank you so much. And make sure you start with your lab 2 in time. And then I'll see you on Thursday.